Hello everyone, and welcome to the first lecture in physics. We are going to start with one-dimensional motion, and let's get started. Well, let's just skip that. So our first topic in physics is to understand kinematics, and this is really essential. Most textbooks, most teachers teach this first. Kinematics is basically the analysis of an object's motion, like how is an object moving. Well, actually, not how. We're not going to talk about how right now. We're gonna describe the object's motion. For example, you might already know some, like, for example, velocity, speed, distance, um, basically describing how the object is moving. Later on, when we talk about dynamics, we're gonna study what causes those objects to move, or how the object moves exactly. But for now, we're gonna understand uh, uh, not how an object moves, but like the like a lot like stuff like speed, velocity, describing the object's motion, basically. So more specifically, when we're talking about an object right now, in this case, we're looking at the motion of particles, okay? And a particle basically is like a point-like object, or an object that you can treat like a point. For example, in some cases, you can treat a ball as a point, or you can treat an electron or a proton or a neutron as a particle, because they're really, really small and they fit with our analysis. For now, we're going to consider one-dimensional motion. We're going to move on to 2D in the next video after vectors. When you talk about one-dimensional motion, I'm pretty sure you heard of one-dimensional or two-dimensional. What does two-dimensional mean? Well, basically there are two dimensions. There's an x-axis, there's a y-axis. This is, two-dimensional. One-dimensional is basically a straight line, a number line. So when we talk about one-dimensional motion, an object is basically moving left or right, or up or down, but not both. Okay? Up or down, up or down, left or right. Alright? So let's get started. So, first we start off with displacement and distance. These are one of the key ways to describe an object's motion, or one of the basic ways to describe an object's motion. So, when you measure an object's position, you measure it with respect to an origin, right? For example, let's say let's say a book is here. If you want to describe its position, you need to describe it with relative to something. Like, you can't describe it relative to nothing, right? If you describe it relative to nothing, it's just a book. You can't describe where it is. So let's say this, and we usually describe it with relative to an origin, like the origin in the Cartesian plane that you come across in math. And this origin, well, this is 1D, so I should not be drawing a plane. I should be drawing a number line. So the origin is given the value, they put the x coordinate 0, hence the name origin. And let's say my book is 5 units, or okay, let's say 5 meters away from it. So you're describing the book's position relative to the origin. So, and 5 meters here is the object's position relative to the origin, and usually you use a unit of distance to describe this, like meters, inches, or centimeters, or kilometers. Usually, for now, we're going to stick to meters. Okay, so what is displacement then? What the word I just wrote down here? What is displacement? Also highlighted here. This should be bolded actually, but for some reason it's not showing up. So maybe PowerPoint's a bit glitchy for me. But what is displacement? So displacement, an object displaces, or there is displacement for an object when the object changes in position. So an object changes in position no matter how small. So let's say this is the origin. My book is here. Let's say this is a physics book. And I decide to move it. Let's say this is 2 meters away from the origin, or 2, x coordinate of 2. Then let's say I decide to move it 4 meters for some reason. I don't know why. So this is an example of displacement. An object is changing its position. We're not gonna be concerned about what is causing this change in motion. We're just gonna be concerned about displacement right now. Because what is causing this, if you're gonna wonder about what is causing this thing to move, you're gonna go into dynamics. I'm not ready to go that in there yet. So the equation that describes displacement is this equation I just wrote down here. That the change in x, this is displacement. Delta it represents change. So displacement is equal to the final position x2, x sub 2, minus the original position x sub 1. So my final position is 4 meters, or 4, x coordinate 4. Actually, I shouldn't describe it in meters, but whatever. And the initial position is 2, so this would be 4 minus 2, so the displacement is 2 meters. Let's say I decided to move it from 2 meters to, I don't know, negative 5 meters to the left. Then the displacement would be, I'm starting off here. Wait, no, sorry, I'm starting off at 2 meters. So 2 meters, x2 minus x1, 2 meters. And then my final position, oh wait, I switched it, sorry. Should be actually, oh no, pen froze. Okay, so let me redraw this. 2 meters, negative 5 meters. So I'm moving it from here to here. Let's not go the other way around. First, let's consider if I'm moving from negative 5 to 2. Okay, then we'll consider from 2 to negative 5 and talk about why displacement is a vector. But first, so the displacement, if I move it from negative 5 to 2, x coordinate, so this would be change in x equal to final position minus initial, 2 minus 5, 7 meters displacement. Now, if I go the other way around, it would be, so if I go the other way around, let's say I go back, then it would be the final position is 5, negative 5, and the initial position is negative 2, so it would be negative 7 meters. And since you are saying you are giving a direction, negative or positive, and a magnitude to this quantity called displacement, displacement is therefore a vector. And I hope you know vectors are basically quantities that have a magnitude, basically its size, and also contain a direction. For example, let's say a boat is going upstream, and you consider that to be the y-axis, and you're going up. So you would say, and let's say you're going at, let's say 60 kilometers per second, or something like that. 60 kilometers an hour, sorry, that was way too fast. Then you're going to say that, actually, this is not a good example. Let's just consider my example that I wrote down here. If you move from, let's say, position x equal to 4 to x equal to 5, your displacement is 1 inch in the positive direction, the x-axis, and if you move from 5 to 4, it will be 1 unit to the left in the x-axis, in the negative direction. So now that we know displacement, change in an object's position, let's talk about distance. And distance is much different than displacement. If you get these two confused, you're gonna get in trouble if you're writing a test. Okay, so do not confuse them. So let's talk about distance. Let me get rid of that stuff. So distance is different. Distance is the amount of area, or not area, amount of meters that you travel, and is a scalar quantity, not a vector. Scalar contains scalars are quantities that only contain magnitude, and they're not vectors. They don't care about direction or anything. So let's do a sample problem and see what I'm talking about. Why displacement, the change in position, is different than the amount of distance the amount you are actually moving. Problem 1. Okay, suppose this blue ball I drew here, this silly looking blue ball, starts at the origin. Let's say I decided to move it to, for some reason, don't ask me why, I decided to move it to 2 meters, x equal to 2. 2 meters to in the positive direction. Then I decided to move it to x equal to 4. Then I decided to move it to x equal to negative 5. What is the displacement? What is the distance? Okay, displacement is, as you remember, the final position minus the initial position. Well, what is my final position? It's not 2 meters. It's not 4. I should get another pen because I shouldn't be highlighting the red. Let's try green. Okay. So the final position, let's first identify where do I finally end up. I start at 0, I go to x equal to 2 at 4, and then I stop at 5. That's what I just said, right? So this is my final, this is my initial. This is my initial, this is my final. So it would be final distance minus initial, so displacement is negative 5 meters. So the object is displaced by negative 5 meters. Now the distance, as you'll see, is different. First I covered 2 meters, then 4 meters, then 9 meters. This is 9. So the distance traveled is 15 meters. Notice, distance and displacement not the same. Displacement is the change in position. It doesn't care where you have been. It only cares about your final and initial position. Distance cares about how far you're going. How many meters are you covering. So that's why those are different quantities. And this distance is usually a scalar quantity, does not need a direction. Displacement is a vector quantity. So in fact, actually the more accurate way of writing this is with an arrow, upper arrow. This is the vector. You're denoting a vector with this arrow notation. Alright, let's move on. Hopefully now you understand a bit, the difference between displacement and distance. Displacement is the change in position. Distance is the amount of meters, how far you're going, okay? Alright. Now, let's move on. Velocity and speed. So, we're going to talk in terms of average first, then we're going to talk about instantaneous, okay? So the average velocity, the overall velocity, of a particle is defined to be the rate of change of position, basically change in displacement over time. Basically, the velocity of an object is its change in position over the change in time. And it has the units, SI units, meters per second. How many meters are you going per second? Velocity, like displacement, is a vector quantity, meaning it also has a direction. You need to describe a direction. In our case, in 1D, it's negative or positive. So this is the formula for velocity. I also wrote it down here. Basically, final position minus initial position divided by change in time. Okay. So I'll just give you some time to take that in. So suppose I start at the origin over here. Okay. This is the axis that I'm moving along. So I'm just going to give you a simple example of how to calculate velocity. You probably already know, but just in case you don't. So let's say I've moved from x equal to 0, and units here are in meters, to x equal to 5. But let's say I'm like a cheetah, and I cover that distance in 0.1 seconds. What is the velocity? Okay. So the velocity here would be change in position, which would be 5 minus 0. The rate change in time is just 0.1 minus 0. So that's 5 over 0.1. That's 50 meters per second, which is very fast. 50 meters per second is around, I think, 180 kilometers an hour, which is actually faster than well, that's actually much faster than a cheetah. It's actually like race car speed, but we're not doing biology here. So the average speed, again, these two are different, average speed and average velocity. The particle is the rate of change of distance with respect to time. Remember, velocity is the rate of change of position with respect to time. Average speed is rate of change of distance with respect to time. It's given by distance. Velocity equals to distance covered over time taken. This formula you're probably familiar with since elementary school, and well, most people know this. So velocity is much different than speed. Right. Suppose if I have a ball, let's take my book again, the physics book. Let's say I kept it on my desk and I moved it, let's say, to another room for some reason. Okay. And over time, I moved it back at the same spot at my desk. But the change in displacement, the change in position is 0 here, so the velocity is also 0. But the average speed is not, because because I'm talking distance here. It's the rate of change of distance over time, not the rate of change of position. So it would be two times the distance between the desk and wherever else I put it, divided by the time taken to do it, and that's the speed, and the speed is not 0. So that's how velocity and speed are different. Speed is rate of change in distance over time, and velocity is change in position over time. So now, instantaneous velocity is basically the velocity at a certain instant. Okay, so for example, let's say I'm driving a car in real life, and in real life you cannot maintain a very constant speed. You cannot maintain a constant speed all the time. So let's say at t equal to 0 seconds, when I start measuring velocity, let's say the car is moving at 20 meters per second, but at t equal to 1, it's moving at 30. T equal to 2, it's moving at 100 or something like that. Okay, so if I want to find the instantaneous velocity, basically velocity at right that instant, at t equals 0 seconds, it would be 20 meters per second. If I wanted to find it at 1.1 seconds, I would have to see the graph of the velocity versus time graph, and use calculus to figure that out. And speaking of velocity versus time graph, we're going to talk about this in the next slide, or I think it's the one after. Basically, a velocity versus time graph is an object's velocity as a function of time. So basically, how is the object's velocity changing with respect to time? And this will be important to understand acceleration and the four basic kinematic equations. Actually, that should be three for some reason. We're going to only cover three for now. Three basic kinematic equations. Alright. And instantaneous velocity and speed, I will cover them in a separate video because they require calculus. And yeah, because not all of us know calculus. Okay, that's an empty slide for some reason. Okay, first let's talk about some velocity. That's terrible. Velocity versus time graph. There's also position versus time, but it's not going to fit our requirements right now. I will actually go over them when I talk about instantaneous velocity, but not right now. So time is in the x-axis. It's independent time t in seconds. And this is velocity in meters per second. It's represented as meters per second. Now let's say I have a car that's somehow magically moving at a constant speed. What would the graph look like? I want you to think about that for a moment. Alright, so the graph would look like something like this, right? It would be a constant function. Because remember, this is this represents the velocity or time, and since the velocity is the same, this would be just a line, a horizontal line with slope 0. Let's say the velocity was changing linearly. That means it's not going all curvy, it's changing linearly like this, meaning the slope is constant. That's just weird. Okay, let me just erase that. I cannot find the eraser. Alright, that should do it. I may need to redraw some stuff. So if the velocity changing constantly, which we'll talk about in the next slide, what this actually means, then the slope is constant, and this kind of problem you can actually deal with, which we will in the next slides. But what if the velocity is changing in some weird way? Then the graph would look like that. It would be all curvy and weird. So this is constant velocity, this horizontal line. This is velocity changing linearly, and this is velocity changing crazily, non-linearly. All right, let's now that you can see what a velocity versus time graph is actually all about, or you can see actually what it looks like. We're gonna move on to acceleration. So what is acceleration? Acceleration is basically the change in velocity with respect to time. Basically, let's look at this equation. Acceleration is also a vector. Acceleration. How much did my velocity change over time? Some people say, if you know calculus, that acceleration is the second derivative of position versus time. Basically, acceleration is telling you how fast are you increasing your velocity. And if acceleration is constant, then the velocity versus time graph will actually look like this. The acceleration is constant. The velocity versus time graph looks like this, with a constant slope, because the slope of this line is, guess what? Change in velocity over change in time. So the slope of this line tells you the acceleration. If it's not constant, then it will look like something like this, or something like that, or something like that, which would look weird. All right. So the units of acceleration is meters per second squared. And just like a velocity, so velocity, as you remember, is meters per second, and acceleration is meters per second squared, or meters per second per second. And this actually tells you what acceleration really means. Change in velocity. How fast are you changing your velocity? That's what it means. How quickly is your velocity changing? Is it increasing? Is it decreasing? Also, so if this value turns out to be negative, that means you're slowing down. That's called deceleration. And if this value turns out to be positive, then it's called acceleration. And if this is negative, then then this v2 minus v1 has to be 0, because time cannot be 0 yet. I don't know, but time cannot be 0. Yeah, v2 minus v1 must be 0 if acceleration is 0. That means the final speed v2 must actually be less than v1, which means you're slowing down. Now we derive the basic equation of kinematics, now that we know the definition of acceleration. Alright, so now let's start with this problem, okay? So now you know how to calculate distance given the velocity and the speed, right? If it's a constant velocity. But what if it's not a constant velocity? We were given the acceleration, time, the initial speed, v1. We're going to refer to the initial speed, or the speed that you start off with, as v1, time as t, acceleration as a. And we're given the distance. This should not be distance, this should be displacement. I don't know why I keep on doing that. Displacement. I guess you could call it distance in some cases, but displacement, so it's going to be referred to as change in x, delta x. So in usual distance, rate, and time problems, you're given speed, you're given time, and find out how much distance you're traveling. Distance equals to speed times time. But now you're given the acceleration, time, and initial speed. So how are you going to do this? All right. For this to happen, let's draw a velocity versus time graph. And this time, very nicely. No messing up. Clear pen markings. Let's draw in style. Okay. Let's see. Oops. Let's do green. Okay. All right. So this is my velocity, or the y-axis. This is the time. Let me label it neatly. Time, t in seconds. This is the velocity in meters per second, also and represented as v. So let's say I start up with some initial velocity v1. As when I start off my analysis, I see the object that is moving starts off with a velocity of v1. Okay, and this is the time axis. This is the velocity axis. So as you know, acceleration is the slope. So let's say my final speed is v2. This is where I stop my analysis, and I connect this dot. Let's assume that acceleration here is constant, very important fact. If not, then you're going to need calculus to solve this. Let me clear. Yeah, okay. So now we want to find the distance. Now if you think about it for a minute, let me just complete this line first. Now if you think about it for a minute, remember distance equals velocity times time, right? So what if I took this? So this area over here must be the distance that's covered, right? Because this is velocity times time. If I find the area over here, or at least the area of this triangle, I'd say this little triangle, let me just label it with another color. I'm going to break this trapezoid up into parts. if I find this area, this must be distance, right? Because it's area under, because I would need to multiply velocity in time to find this area, which is distance covered. So when we find the area of this trapezoid, we're actually finding the distance that is covered by the object. And when we find this, the area of the trapezoid, we actually get a very useful formula. All right. Let me just finish with the red. I don't want this green anymore. If you remember, whoa. Okay, that wasn't supposed to happen. That was weird. Let's just give it time to reboot. PowerPoint kind of crashed. Okay, this might take a while. Alright. Fully okay. Did not save my annotations, did it? Alright, I'm gonna have to draw the graph again. Sad. Oh, my pen is not working anymore. Wow. 2 disasters in a row. Alright, hopefully it works now. Apple always works. Alright. So this is the time axis again. In seconds, hopefully. I'm not going to write that down just to save time. Velocity. V. Okay, this was V initial. This was V final. Now we find the area of the trapezoid to find the distance that is covered. This, as you remember, is acceleration, this slope, this value. So how do we find this, find the area of this triangle? Well, we do height times distance, right? Height times distance. But I would like to represent this in terms of acceleration. So if you were actually to find this without using acceleration, you could do it. You would get, let's say, what's the formula for trapezoid? This is v1, no, this is v2 minus v1, and this is v1, so this whole thing is actually v2. So it'd be v2 plus v1 divided by 2 times the height, which is t, which is change in time. So that's one formula, actually. This is the first formula that we did. Second formula now. We actually represent in terms of acceleration. Acceleration, as you remember, would be v2 minus v1 over t2 minus t. Let's just write it that. Yeah, t2 minus t1. Or since t1 here is actually 0, so let's just write t down there. This is just t. So when we're multiplying, so when we're multiplying, now when we're actually talking about this in terms of acceleration, let's consider this in parts now. Let's add the area of the triangle and this rectangle. Area of rectangle, easy peasy. This is just t times v1. Now this. What do we do with this guy? I'll let you think about this for a moment, actually. See if you can figure it out. Well, how would you represent this distance in terms of acceleration? So I'm not going to let you pause. I'm just going to give you 1 minute to think about it. Alright, if you want to represent this area in terms of acceleration, remember the area here of this triangle now, we're talking about the triangle because we decided to split it into parts, you'll see why in just a second. Then it would be v2, why is that v2, minus v1 times time. And we know that acceleration equal to v2 minus v1 times time. So if we multiply each side by t squared, then you get 8t squared plus equals to v2 minus v1. Oh, forgot the half. It would be half here. So this would be, so at squared here actually equals v2 minus v1 t. So at squared, or more precisely half at squared, sorry, I forgot the half, I can't. So half at squared would be half, so half at squared is actually the area of this triangle now. And let me highlight that in red so you can actually see it. So half at squared is now the area of the triangle. And I actually didn't memorize this method when I first learned this formula. I just did it on my own. I just figured this out. So what I did basically here was I had a equals to change in velocity over change in time. I multiplied both sides by t squared, and I got t squared a, or at squared, equal to v2 minus v1 divided by t times t squared, and I get this. So I forgot the half, so I should probably include that, since you have the half in the area of the triangle. So this becomes half at squared equals to half v2 minus v1 times t, or change in velocity times t, which is the area of this triangle. So the area of the triangle is half times acceleration times time squared. So the distance can also be the distance traveled with acceleration, initial speed, and time given is equal to the initial speed v1 t plus half a t squared. And we have a second formula that also does that. When we consider this, when we actually calculate the area of the trapezoid, and not break it apart into parts, would be v2 plus v1 over 2 times time, tangent time. I forgot the squared. Yep, and there we go. This is one of the two formulas. The third one is actually this one. So let me write that down. Third one is a equals change in velocity over change in time. That's considered to be third. Now the fourth. What if you don't know the time? What if you only know the final and initial speeds and the distance and the acceleration? Or actually the three of those values, and you want to find the remaining one. How do you do this? Well, we substitute for time. Let's take this to the next slide. Okay, so let's figure this out. So we have displacement equal to initial speed times time plus half AT squared. We're actually going to need only two formulas here. We want to substitute for time. What if you don't know time, right? So time equals, so if you remember, I have to keep on getting out the eraser. Alright. That acceleration equals to v2 minus v1 over t, correct? So now we just solve for time and see the magic that happens. So now we substitute for time. Equals v1, so v2a plus half a v2 minus v1 squared over a. Okay, so this is going to take up space. Maybe I have to make another slide or something. So this is v1 v2. It might sound stupid I'm expanding, but it's actually very helpful, as you'll see. Half a. This a cancels out with the a squared below, so we get an a in the denominator. V squared minus v2 squared minus 2v1 v2. Oh, wait a second. Sorry, 2v1 v2, yeah. Plus v1 divided by a. Multiply a both sides. 2, not 2. Sorry, a equals v1 v2 minus v1 squared. We expand the half. Well, that's some terrible plus sign. So I'm just gonna write expand out this plus half v1. Oh, look at that. That cancels out. We can subtract this with this, so you get change in x equals half v2 squared minus half v1 squared. Multiply 2 both sides. You get 2 displacement times acceleration equals to v2 squared minus v1 squared. You could either leave it like this, or you could take the v1 other side, and you get v2 squared, or the final speed squared, equals to the initial speed squared plus 2 times the displacement times acceleration. Very useful formula. That's the third. Wait, that's the fourth, sorry. So let me just write them all down in different colors. First one. Actually, all of them are important, so I shouldn't be saying each one is important individually. I'm just going to say all 4 kinematic equations are important. So the first one, change, well, okay, is that, hopefully you know what v1, a, v2 is all about now. Okay, a equals, that's not the right one. A equals to v2 minus v1. Oh, that's not the right color. I did that again. And I need to fix that too. v2, 2. Oh my god, this is just terrible. Can't write down properly. Okay, that's v1, not v2. Okay, another color. A equals to v2 minus v1 over t2 minus t1. Now a blue one. Let's do this. v2 squared equal to v1 squared plus 2 times delta x times a. And the fourth one was, I believe, change a displacement equals, what was the fourth one again? v1 plus v2. I don't bother memorizing these formulas, only some of them. One thing about physics you should know is that You should only memorize the most important formulas. I usually memorize this, this, and this. This one I usually don't need, although who knows. But more than memorization, you should know how to derive them. You should know where they came from. You should know why they exist. All right. So those are the four kinematic equations relating acceleration, initial and final speed, displacement, and time. Next week, or next video, sorry, not next week. Next video, we're going to talk about vectors and free fall acceleration. What happens when you actually drop a ball? What's its acceleration? What happens over there? And yeah, so now let's look at some problems. I'm just going to come up with some random problems. Oh, I don't have any time. Oh, hold on. I don't have any more slides. Uh-oh. I'm just going to leave this up. Or I can pause the video, whatever. Alright, so I need a empty slide. Okay, let's do a problem. Let's do a problem. Alright, let me think. So let's suppose I have a car. I'll suppose I have a block, okay? And it's somehow magically moving, somehow, let's say suppose Doctor Strange, alright, is somehow moving this block. So time equal to 0. So let's say this block has an acceleration of about, 10 meters per second squared. This block starts out 10 meters per second squared for 5 seconds with initial speed of 0. But at the end of the fifth second, it starts deaccelerating at a rate of negative 5 meters per second. And it takes it 2 seconds to stop. Wait, no, that doesn't make sense. Not 2 seconds. Okay, yeah. So it starts deaccelerating at negative 5 meters per second, and you'll just see why I removed that 2 seconds there. I actually did that on purpose. I guess I added 2 seconds, but then I just removed it. You'll see why I did it. It's not actually 2 seconds. You can actually determine how much time it takes for it to stop. After it starts deaccelerating, after 5 seconds, t equal to 5 seconds, at a rate of negative 5 meters per second. Alright, so the question is how much distance does it travel in this acceleration and deacceleration? So we break it up into 2 parts. First, how much distance does it travel in the first part? Alright, how much distance does it travel in the first part when it's accelerating? So that would be change in x. Since initial speed is 0, you can ignore the initial speed times time. That's just 0, so this is just half a squared. In many cases, the initial speed will be 0, so you can just use this formula. So it would be half 10 times 25. This is 125 meters. Now it starts slowing down. Alright? Now it starts slowing down. We want to find the distance. So let's find the velocity at t equal to 5 seconds. The velocity, so a equals v2 divided by t. So v2 equals 10 meters per second times 5 seconds. So the velocity at the end of 5 seconds when it's done accelerating is 50 meters per second. And then it starts deaccelerating at this rate. Now we can use this formula. V final squared equals to V initial squared plus 2 times this times acceleration. We know this is 0. So we get negative v1 squared equal to 2 delta x a. Substitute it. Now here a is negative, so the negative and negative will cancel out. So the distance is positive, thankfully. So this would be negative 50 meters per second squared. So distance would be that negative 50 meters per second squared divided by 2a. So 2 times 10 meters per second squared. This would be, so this is also negative, so negative, negative cancels out. So this would be 2,500 divided by 20. So it would be 125 meters. I hope my math is correct. If not, then I don't know what to do. So guess what? It's the same distance as we traveled. Wow. Surprise, surprise. And I just made up this problem. So distance covered accelerating is the same as distance covered deaccelerating. Notice I didn't find the time that would take in an extra step. I just used this formula. Oh, I didn't write that in the formula, did I? Oh, yeah, I just used this formula. So, yeah, this is the thing in kinematics, especially if you're giving Olympiads, that you should use the most efficient kinematic equation, although in most Olympiads, you don't need them. But whenever you're solving a physics problems in kinematics, you should use the most efficient formula. And that's why I suggest you should memorize them, but also, more importantly, understand where they're coming from. So, let me just check if my work is actually correct. So I didn't make a dumb mistake. So V2 is, okay, 50 meters per second. Okay. Alright, everything seems good. So the total distance traveled is 250 meters. Or about 1/4 of a kilometer. So don't accelerate this fast, okay? Don't accelerate this fast and don't deaccelerate this slow. You're gonna need a half a kilometer to stop. Alright, in a car. So don't accelerate too fast in a car. Leave those to the cheetah. Alright, see you. So that's the end of the video. And see you.